behalf of the BURSTT team, I'd like to present a system overview and site development of the BURSTT, one of the FRB project in Taiwan. The project is a collaboration of many institutes, and it has been funded by the National Science and Technology Council of Taiwan. And we also got lots of support from the academia scene. Here I show a conceptual design of the BURSTT main rails 256 element. In today's talk, first I will give you an overview of the system. We can divide the system into front end and back end. I will describe the front end in more details, and then for the back end, please refer to Kairos. Then I will describe the site development we have done so far, and in the end, I'll describe the expected timeline of the project. In phase one, we plan to set up a main array with 256 elements, together with several outrigger stations. In the parameter plot on the right, the BURSTT is in the large field view region to monitor more sky. Based on chimes detection rate, we expect to detect about 100 FRB per year. With outrigger can provide VLBI capability for FRB localization. And for more detail about the project, I'd like to refer you to Shoshen's paper in PSP. Here I show you a system diagram of the BURSTT main array. We'll set up a 16 by 16 array with 1 meter spacing, corresponding to one wavelength at 300 megahertz. The RF coverage is 300 to 800 megahertz, with a signal bandwidth of 400 megahertz. We will use a single polarization LPDA antenna with a 9 dB gain. The field of view is about 60 by 60 degree, and the system temperature is about 50 K. The front end includes the PDA antenna, front-end electronics, and signal transmission on the front end to the back end. I will describe each part in the following slide. We have designed a log periodic dipole array antennas to cover 300 to 800 megahertz with a 9 dB gain. On the radiation plot, the 3 dB beamwidth is about 60 degrees, and the return loss is less than 15 dB within the frequency band. The reason to come out with your own design is to you can modify it to optimize the performance. For example, we plan to integrate the low noise amplifier to the antenna design to further reduce the system noise. We have fabricated design. We also bought several commercial antennas, and we have been testing them on top of building before deployment. And our NTU colleagues also working on some antenna development. for array of large number of antennas in the future. They are the planar LPA design, also the magneto electric dipole antenna. In the front-end electronic, there's some filter to remove the FN and the 4G signal. Also the low noise and RF amplifiers. The key component of the front-end electronic is the low noise amplifier. We're using the one from mini circuit with a noise figure of 0.4 dB. The photo in the lower left show you how the front-end electronic are assembled in the waterproof box. Here's some detail about the, and then we can come back to this later. For the data transmission, we are using the coaxial cable at the moment, but we are developing RF fiber to transfer signal to a place away from the site, so we don't have to worry about EMI issue of the digital electronics. We also adopt the CWDM technique to transfer several signals over one fiber. We've done some preliminary testing of the RF over fiber system, and we measure the transmission and reflection of the system using a network analyzer, and the results are promising. Regarding the data processing, it's for an array of regularly spaced antennas. First, it's computationally efficient to do FFT beamforming. When the number of the antennas is large, and the computational cost scales n times log n instead of n squared. So we'll do the FFT beamforming instead of cross correlation. In the back end, we use RF SoC and the FPGA to digitize and channelize the time domain signal from the antenna. We can also do 1D beamforming and RFI removal using FPGA. And the second beamforming and the dispersion are carried out in the server. I'd like to refer you to Kyle's talk for the back end later on. For the site development, we have surveyed around the island. There are 4 candidate sites. We will set out the main station at the Busan Botanical Garden and the 3 other outrigger stations. Each site is about 100 kilometers away from each other, which can give you about 1 arc-second angular resolution. We are doing some preliminary tests at each site, and we also construct some infrastructure for the main station. We also plan to set up some outrigger station overseas to provide much longer baseline. For site development in Hawaii, to refer to intent talk. We'll set up the main station at the Busan.
Few minutes left.
Okay. We set up the main station at Fushan Botanical Garden. We have surveyed the garden to find a place with minimum Wi-Fi. At site number 6, there's only some TV and 4G signal. This where we will set up the main station. And since there's no power in the network connection at the site, we pull some power and optical fiber cable from the entrance to the site. And these are some photos taken when doing the cable and the installation. We also set up a platform there too for antenna and the outdoor cabinet installation. So in the following slide, we're going to show you what we have done in several outrigger stations. First one is along the northern coast of the island. This one's on the Green Island Research Station. And this one's carried out by the NTU people in central Taiwan. And we just visited Dongsha recently, and it's a coral island. And the Wi-Fi condition there is optimum. The timeline, we completed the infrastructure of the main station last year. Beginning this year, we will start to set up 16-element array in the main and the outrigger station. And we will then continue expanding by adding more antenna and the instrument. Okay, so that slide is our goal. Thank you.
Thank you. Do we have questions? Come back.
Hello, thank you for your nice talk. And I am curious about what's the difference or the advantage of LPDA over the antenna with discs.
LPDA antenna has large field of view compared to dish antenna.
Oh yes.
Yeah. The field of view is larger.
Why?
Because
it's diffraction limit. So a big telescope, like, I don't know if you know what the FAST telescope in China, it's got 500 meters size. So if you want a big dish, that's a big dish. It only sees a few arc seconds. So it only sees a tiny amount of sky because the resolution of your telescope increases and your field of view decreases. So big telescopes see very little sky, small telescopes see a lot of sky. And no telescope sees the whole sky.
Hello, thanks for your nice talk. Can you go to the 8th page? Page 8. Well, I want to ask something in detail. I'm so curious about on the left hand side. They are far different from the simulation. Do you have any idea about it? Yes.
Okay, maybe 10号跟answer that.
Sorry, so what's the question about the antenna?
Oh, well, over left hand side, as we can see, here's somewhere far different from the simulation. What happened?
Could you use the microphone? So that people can
Do you mean the per side at the bottom right?
Bottom right.
Okay, so currently, I think there are two folds. One is the simulation. Currently we just do a rough simulation. So the resolution. The y-axis is the log scale. So below that, I think it's minus 20 dB. I think our simulation currently don't have enough resolution. And the second one is the measurement. Also, we just did a quick measurement at the open field. So I think there's lots of interference, etc. So in the future, after further development, I think we'll do a more careful calibration inside an encode chamber. Yeah, so we might get a more consistent result.
Okay, thanks.
Yeah, thank you.
Okay, thank you. We have to move on to the next talk.